SP9a, objects affecting each other. You need to basically be able to list any contact or any non-contact forces. So first of all, if you have a look at the list of contact forces, we have things like tension, friction, upthrust, air resistance, water resistance, the normal contact force, or abbreviation NCF. So the normal contact force is any force between a surface and an object which is at 90 degrees to the surface. So the word normal in normal contact force represents the fact that it is 90 degrees to the surface. If the surface is horizontal, for example, the normal contact is vertically up. If the surface is vertical, and you apply a force on that surface, the normal contact will be back out of the surface horizontally. Or if the surface is slanted, it will be 90 degrees to that surface, depending on the angle of the slope. All right, and that's the normal contact force. Air resistance we've had, water resistance, any forces which require contact between the two objects in the interaction. The non-contact forces, all we have are gravity, electrostatic force, and the magnetic force. So those three forces can apply a force on other objects without actually having any contact between the two. So for example, the gravitational force, you have any object with mass. We're going to look at those fields a little bit more in a second. The electrostatic, you have the charged particles, and then the magnetic, you have magnetic materials, iron, nickel, cobalt, for example. All right? Before we get into the non-contact forces in a little bit more detail, we actually have to make sure we understand Newton's third law. You need to understand all three laws, and we've made videos on that in chapter 2 in the first paper. But the third law is very, very crucial in understanding the non-contact forces, for example, and also the forces between two objects in contact, one of which may be the normal contact force. So Newton's third law, definition: every action has an equal and opposite reaction. So the action is a force, where an object applies a force on another object. That opposite object will then apply the same size force in the opposite direction on the same object. So the Newton's third law, the two objects that apply equal and opposite forces have to be between the same two objects. You can't have a third object, for example, coming into play. So if there is an object, the most complicated situation for Newton's third is if you have an object on a table, or any object resting on a surface. Now the reason the object is resting on the surface is because the Earth is pulling that object down. So the weight of the object, as you can see in this diagram with the apple, the weight of the object is down. If that's your action, then the reaction has to be between the same two objects. If the weight of the object is being provided by the Earth, that means the Earth is pulling the pen. If that's the two objects involved, the pen and the Earth, then the reaction force has to be between the same two, pen and Earth. So if the weight of an object, any object, bag on a table, chair on the floor, okay, anything on a shelf, if the action force is the weight of the object, which is Earth pulling object, then the reaction force has to be the gravitational pull from the object on the Earth. Alright, so in this situation, if the weight of the object is the action force, the reaction is that apple pulling the Earth up. Okay, same size, opposite direction. However, you sometimes see the normal contact force from the table on the pen, which is the most commonly mistaken force as being the action-reaction between the weight of an object and then the reaction is the table on the object. That's not true. But if the normal contact force is the reaction, then you have to have a different action. So, in this situation with the pen on the table, the normal contact force is the force from the table pushing back on the pen 90 degrees to the surface. If that's the reaction in this situation, then the action has to be between pen and table. Because if the reaction is between table and pen, the action has to be between pen and table. So in this case, you would say the action is the force from the pen on the table. In which case the reaction is force from the table on the pen, and we know that as normal contact force. That's the only way that normal contact force can be involved in the action-reaction. If action is weight, then it has nothing to do with the table, it is earth and pen or earth and object. Alright, that's Newton's third. In order to draw an interaction diagram between two objects that are applying forces on one another, then you have to draw the two objects with forces which will be in opposite directions. So between the Earth and the Moon, the Earth applies a force on the Moon, which is pulling the Moon towards the Earth, and therefore the reaction is the Moon pulling the Earth with the same size force in the same or opposite direction, but both towards one another. Same size, even though the Earth is bigger and has larger mass, its action-reaction, they have to be the same size. So this is a force interaction diagram between two objects. Just two lines, the right direction, the same size. Looking at the three non-contact forces, gravity, electrostatic and magnetic force in more detail, we know that all three of those things can apply forces on other objects without actually touching them. Now there must be something in between the two that causes that force interaction. To experience a force, you have to have something. Now we can't see it. It's something invisible, and we call that thing a field. So a field, by definition, no matter what type of field, G, E or B, the space around an object wherein an object experiences a force. So if another object enters the field of something that has its own field, gravitational, electric or magnetic, if an object enters that field, then it will experience a force. Alright? The three types of field we have are G field, gravitational field, which affects any object with mass, and only mass. The E field, which is the electrostatic field, which affects any object with charge. Or you have a magnetic field, which we call a B field. The reason it's called a B field is because the magnetic field strength, the symbol is B. So G for gravity, E for electrostatic, but B for magnetic field, which only affects objects which are magnetic materials, as we said, iron, nickel, cobalt, or permanent magnets such as ferrite, alnico, all of those. Now, going even deeper into the three types of field, we said only affects mass, gravity, charge for electric, and magnetic materials for magnetic fields. You have different types of field as well. The first type we're going to look at is the radial field. If you move away from the Earth so that you can see the Earth as a sphere, then the field, the further away you go, the strength will get weaker and weaker. Now the way that we draw that is by drawing field lines that are along the radius of the sphere from the center of the sphere, hence the reason it's called a radial field, because the field lines are drawn along the radius, and as a result, the further away from the object you are, the further away the lines are in the diagram, which represents a weaker field. So we know if you go further and further and further away from the Earth, the strength of the gravitational field will become weaker and weaker. And how do we draw that? If we draw the lines along the radius of the sphere, then they get further and further away from each other, which represents a weaker field. So this is a radial G field. Now the direction is very important. If you're going to draw arrows on your field to represent which direction would the force be if an object were within that field, gravity is always attractive. Gravity will always attract mass, it will never repel. So the arrows for a gravitational field are quite straightforward, they're always in towards the object. So this is a radial field for a gravitational field, arrows pointing towards the center of the Earth. If you wanted to draw a radial field which was stronger than another radial field, for example the field for Jupiter or the field for the Sun, then all you do is draw more field lines on the diagram. Same diagram, force arrows inwards towards the object and the lines going along the radius, getting further apart. But if you have more lines, if you have a larger concentration of field lines, that represents a stronger field. Okay? Just like if we wanted to draw the moon's field, then we have fewer lines. Still along the radius, let me give you an example. If this were the moon, you might only draw 4 field lines going in. And as you can see, that is clearly weaker than the Earth's gravitational field. There are fewer lines, but it's still a radial field because the further you go, the weaker it becomes. A proton field, because charged particles we assume are spherical objects, we draw their fields if they are isolated, so I just have a positive charge on its own. It has its own field because it's charged. It has its own electrostatic field. But for a proton, which is spherical, also has a radial field, exactly the same as the gravitational field, except the direction is different. So for electrostatic fields, E fields, affects charge only, but they can both attract and repel. So which is different to the G field, which only attracts. Electric fields can attract or repel. Now how do we draw the direction on the field? If it's a positive field, we assume there is a positive charge inside it. So everybody agrees on the same thing. When we want to draw the field for an electrostatic field, positive or negative, we always assume there is a positive charge inside the field. In which case, if there were a positive charge inside a proton's field, then it would repel. Positive and positive would repel, so we draw the force arrows pointing outwards. For the electron, obviously, same spherical object, even the same size charge as a proton, relative charges are +1, -1. So this radial field is the same strength as the proton field. It's radial, so the force, the lines move further and further apart as we go away from the electron, so it gets weaker. But the direction, if we assume again that there is a positive charge inside the electron's field, then it would attract the positive, so the electron field goes inwards and the positive field goes outwards, and they both attract and repel charged objects. Alright, they're your radial fields. Moving on, we have the opposite, which is a uniform field. A uniform field literally means it has the same strength everywhere. And how do we draw that? We draw parallel field lines with the direction again, but all lines are parallel with the same spacing between them. That represents a field which has the same strength, no matter where you are in the field. You can have a uniform field for the Earth. If you come close enough to the Earth's surface, as far as we're concerned, it's a flat surface. So the field lines, as you zoom into the surface of the Earth, are parallel lines. We experience the same strength, no matter if we're downstairs, we're at the top of the building, you could be in an aeroplane and the gravitational strength wouldn't change that much. Until you get far enough away that you can see that the Earth is a sphere, does the strength start to change. So for all intents and purposes, at the surface of the Earth, the strength of the field is the same, therefore it is a uniform gravitational field. Field lines parallel, all pointed towards the Earth. Uniform electric field, simply a battery. You have one plate which is charged positive, one plate which is charged negative, and the field lines between the two are parallel, same distance apart, therefore the strength is the same, and the direction is positive to negative. Finally, you can have a uniform magnetic field. So you could have a bar magnet that has these two poles, two magnets here, spaced evenly parallel between them, north and south, and you have the field lines going across in the direction from North Pole to South Pole. We haven't looked at a radial magnetic field, and the reason is, if we look at the magnetic fields that we have for shapes that we're aware of, a bar magnet, for example, the most simple magnet that we have, a rectangular magnet, has both north and south poles. So magnetic fields only affect magnetic materials, and again, magnets can attract and repel. So they're similar to the electric field, unlike the G field. But a bar magnet, the field lines come out of the north, and they loop back inside the other pole of the magnet. They don't continue forever, like the G and the E fields. Just like the Earth's magnetic field, the Earth is a sphere again, but the magnetic field lines, they come out of the pole, they come back in at the other pole. Now, strangely enough, the Earth's magnetic field actually doesn't come out of the top of the Earth and go down to the bottom of the Earth, which we call north and south. The magnetic poles of the Earth are upside down. So the north of the magnetic pole of the Earth is at the bottom, south is at the top, so the field lines for the magnetic field of the Earth are actually coming from the bottom to the top. So the north pole magnetic pole of the Earth is at the bottom, and south magnetic pole is at the top. And the field lines come out and they go back in, similar to the bar magnet. So you can't have a radial magnetic field because they have to leave and come back. There is not just one pole on the magnet, there's two, so it comes out and it goes back in. So no radial field in that case. And very, very finally on this chapter, you could be asked to look at the field interactions. So the force interactions between two objects are just two force arrows either pointing towards each other or pointing out if they're repelling. Just the arrows. The field interactions, on the other hand, are how do the fields combine if two north poles come together. We know that they repel each other, and they repel with a force that we can't see. Something must be going on between the two fields. And what's happening is, because they're the same direction, they're both north, the field lines will not cross over. They cannot. You try and force those two fields together, and they will do their very best to deflect one another, and they will not touch, they will not cross. Okay? So north and north, the field lines are out from the north. Remember, it comes out of the north and into the south. They will be going away, but they will curve in the middle to stop them crossing over. On the other hand, if you have a north and a south, which we know will attract, then the two fields actually, they do interlink. They'll cross over one another, the field lines will come together, and they will cause that attraction which will bring both magnets together. That's what attraction is. So these field lines cross. Same thing if you have electric charges, positive and positive. The fields push together. Again, they will deflect. They will not want to cross. They will push each other away. And again, the field lines won't touch. And if it's positive and positive, they're going outwards. Okay? This is the same diagram if you had negative and negative, except the force arrows would be the opposite direction. Because electrons, the arrows go inwards. The same diagram would apply to negative, negative, but the arrows would be going inwards. And finally, if you have positive and negative charges, in the middle, again they will cross over, they'll come together, and on the outsides of the charged particles, there'll be the same radial lines that are unaffected by what's going on in the middle. Okay? So they're field interactions. How do the fields of two objects actually interact? Do they cross over to attract, or do they deflect when they try to repel? You have the two types of force, Newton's third law that applies to these forces, the fields, definitions and the types, radial, uniform, and then your magnetic fields. And you could be asked, for example, to describe the differences and similarities between two fields, between all of them, or to draw these force diagrams and the interactions between the fields, or just the force interaction between the two objects.